Okay. One, via partiti. Okay, so actually, I want to start with an advertisement sketch. My book is out. I'm very happy. So, The Order of Time, and also in French, L'Ordre du Temps. I just received the British one, and the French one I got in Paris yesterday. So, everything you want to know about time, if you're not happy with the lecture I gave here, it's in those books. So, now we're going a little bit more technical. So where are we? So this is GR. Is B wedge F, where this is a functional of B and a connection. The connection is an SL2C connection. B is an SL2C two form. F is a curvature of omega, and on the boundary, so this is sort of the bulk, we have SUT on the boundary. B restricted on the boundary has an electric and magnetic part, which I call K and L, which are related by this equation here on the boundary. And the boundary breaks SU2 SL2C down to SU2, SO3 down to SO31 down to SO3, Lorentz down to rotation. So there is this structure on the boundary. This we're going to use. And to go to the quantum theory, we need we're going to write Hilbert spaces, of course, and not surprisingly, these Hilbert spaces will carry a representation of these groups, like always in quantum mechanics when you have representations, some symmetry. And we will have unitary representations of this group. So let me do a little bit of math. It's going to be useful in any case, which is SL2C and its representations. And this I'm going to use heavily the things I introduce here. Now you may think, oh, we know everything about Lorentz. I mean, we are physicists who have been hammered on our head Lorentz since childhood, and we know it all the way around. But actually, quite remarkably, the representations of the Lorentz group, or SL2C, that we physicists use are not the unitary representations, or the finite dimensional representations, which are not unitary, because SL2C is a non-compact group. And its unitary representation are infinite dimensional. So the unitary representation of SL2C are not much known by physicists. In fact, they're almost unknown by physicists. They've been worked out by mathematicians back in the 60s, 70s. There is a book by Ruhl, or UHL, in the 70s, which has all the mathematics in, but is not sort of mathematics which is known by physicists in general, but we need it. We need it to set up the theory. In fact, loop quantum gravity, if you want, is based on unitary representation of SL2C, which surprisingly are not part of the standard tool of theoretical physicists. Surprisingly, because I mean, quantum gravity, it's quantum, so it's unitary representation, and its gravity is SL2C, so it seems obvious that that's the right language for talking about these things. So let me start slowly from SL2C. So SL2C, I write group elements of G in SL2C, and as I did for SU2, I just follow the discussion SU2. We can think of this as a group, a group of matrix elements, A, B, C, D, which, however, they're not unitary. So if they're unitary, the subgroup is here. The only conditions here is that the determinant of G is 1, which again is a complex equation because this is 4 complex numbers, so it's two real equations, so it's 4 complex number minus 2 conditions is 6 parameters, so it's a 6-dimensional group, obviously, 3 rotation and 3 boosts, if you think in terms of Lorentz transformations. And remember that an SU2 group element can always be written as the exponential of a linear combination of Pauli matrices with an I here and 3 real parameter alpha 1, alpha 2, alpha 3. If you take this 3-parameter complex, you get a 6-parameter kind of things, which is the generic SL2C group element. So 3 complex alpha here parameterize locally SL2C. And if they are real, you are in the SU2 subgroup. If they're complex, if they're imaginary, you have 3 boosts. The generators are usually written in the adjoint representation, so in the IJ. So IJ, these are Lorentz indices antisymmetric. This is equal to minus IJ, and they have the SL2C algebra, which in its covariant form is this. I never remember because I never use it, but let me just copy. It's just Minkowski metric, otherwise you get SO4. So minus IKJLK plus eta I, no, sorry, yes, IKJL eta ILJJK minus eta JK JIL minus eta JL JIK. There's a more decent way to write it, which I'll do in a moment, but this is a covariant way of writing it. It doesn't depend on the choice of an SU2 subgroup inside it. Now, if we pick an SU2 subgroup.
The last term was minus or plus?
Minus, plus, minus, plus. Thank you. So it has to be antisymmetric in IJ, antisymmetric in KL. So it's basically the first one, antisymmetrized in IJ and antisymmetrized in KL. Now, if I pick an SU2 subgroup, I break SL2C diamond SU2, which in this language here amounts to pick a time direction. Choose a Lorentz frame, so choose a time direction. I can always choose coordinate, which is this 1, 0, 0, 0. Okay, so I can break the generator in the electric and magnetic part, the rotation and the boost. This is what we have seen before when we were talking about the B. So I have Li defined to be I, J, K, L, J, J, K, T, L. So if I take T having that form, usual definition is 1/2 here. If I having that form, this means that this is only different from 0 when L is 0. So if I is 0, this is 0. So again, this is 0, and some vector L, L1, L2, L3, and its brother Ki, which is just JKL TL, which is also 0K. So I take the electric and magnetic part of this, and the L, I, Lj are just a standard generator of rotation, Ij, K, Lk. So this is SU2, the SU2 that sits inside Lorentz. And instead of this thing here, Li, Kj, just tell me that the K are vectors under the action of a rotation. So this obviously is epsilon Ij, K, K, K. Okay, so this.
I'm sorry, Carl. The definition there is Ki equal what? JIL contracted with TL?
TL.
Right, and it's okay.
Thank you.
I mean, you can define these objects for any T. You don't need.
You can define for any T, and if you choose T like that, or if you adapt your coordinates to T, then you just have the space component of that in your coordinate. Otherwise, you have a linear condition between them. What I'm pointing out is the 3 of these and 3 of these, not 4. And Ki, Kj is epsilon Ijk Lk, right? So the commutator of 2 boosts is a rotation. If you boost in an x direction and a y, and then in a y direction, or if you do the other way around, you get the same boost but a rotated frame. So the geometry of the Lorentz things. And this Lk are not by chance named the same manner in which I've named Lk when I was talking about general relativity. That's why I'm going slowly in these things. Now, there are 2 Casimirs. It's rank 2, so it's a 2 Casimir. Remember that with SU2 we had 1 Casimir, which is the square of L. So here you want something which is invariant under SL2C transformation, and the 2 Casimirs are the square Jij, Jij, and Jij, Jij star. So the 2 Casimirs are, you can write them as Jij, Jij, this is 1, and the other is epsilon Ijkl, Jij, Jkl. And equivalently, if you write them in terms of L and K, they are L square, K square minus L square, and K, the scalar product. So this I call C1, this I call C2, which is which I don't remember. So.
The commutator of K is epsilon Ijk K or?
No. L. The boost does not form a rotation. The boost is not a subgroup. The rotation is a subgroup, but the boosts are not a subgroup.
So if I combine 2 boosts, then I subtract them and rotate.
Yeah.
Okay.
Yeah. You might sit down and think physically, and it actually, it's so. Right, yes. Or you might do with Pauli matrices here. I mean, it's definitely so. Real is real imaginary is imaginary, imaginary is real. Okay, so, and then you put the minus where it goes. I'm not sure the minuses are right in my things. Don't. As I said at the beginning, don't take my minus and my 1/2 from the blackboard and then rely them. If you want to look at the books, they're written correctly. So there are 2 Casimirs, this one and this one. I don't remember if there are 1/2 between the 2. Let's say this has to be this one, right? Because the minus come from the Lorentz metric from the 0, and so this one is this one. And let's talk about representations of SL2C. Now, you all know the finite dimensional representations. The simplest one is the fundamental. So the group elements G act on a vector space, which is C square, which is spinors. So it's Z0, Z1, two complex numbers. And it acts just with the matrix that I just gave before. Okay. So it's the same vector space as in the fundamental representation of SU2, but careful, it's not the same Hilbert space, because in the fundamental representation of SU2, this was an Hilbert space with a scalar product. Let's call this Z, ZW. Remember, this is ZA bar, WB, delta AB. Okay, and this is invariant in SU2, because if you act with an SU2 matrix here and you act with an SU2 matrix here, the matrix is unitary. Being unitary means if you bring the other side, it becomes -1. Okay, it's a transpose because it's the other side. It's a bar, so it's a dagger, and so U dagger is 1 if it is in SU2, but not if it is in SL2C. So therefore, this is not SL2C invariant. So you say, well, is there another scalar product here which is SL2C invariant? No, there is not. Okay, this is not a unitary representation of SL2C, and in fact there is a general theorem that says that a non-compact group doesn't have finite dimensional unitary representation, so this cannot be. Okay, but remember there was another antisymmetric quadratic expression here, which is ZAWB epsilon AB, and this was invariant at SU2, is also invariant at SL2C, because if you remember, when I showed that this is invariant, I only used the fact that the determinant is 1, not the unitary. So also if you act with G here and G here, you get the same number. So this is a structure which is SL2C invariant. This is not a structure which is SL2C invariant. Okay, this breaks the SL2C down to SU2, this scalar product here. And in fact, the scalar product, writing this scalar product of spinor space is like choosing a Lorentz frame. We'll see even more cleanly when we write this, the map to four-dimensional vectors. What is this? Well, this is a fundamental representation of SL2C, and from the tensor product with itself, the tensor product with itself contains an invariant part. Here is the invariant part, easily, like before. This is one representation. You know many other representations, and in particular, you know Minkowski space. Minkowski space is a the object here VI, I is 0, 1, 2, 3, 4, and there is a map from SL2C to SO31, exactly like SU2. SU2 is not a one-by-one map. Is mapped to four-dimensional matrices, and it's exactly the same formula as the one with SU2, but now you have 4 Pauli matrices, the fourth one being just identity. And the identity is the one that defines the scalar product. So to say which one is identity, in the linear combination of the 4 Pauli matrix, to say which one is time. It's like defining a scalar product. It's like fixing a Lorentz frame. It's like making this a Hilbert space. Is like reducing SL2C down to SU2. I'm not, I could go on. There's another representation which is Fij, right? The electromagnetic field, which is a joint representation, is the one in which the algebra lives. These are all finite dimensional. And then there's the scalar representation. These are all finite dimensional. These are not the ones finite dimensional representation. These are not the ones we need. We need the infinite dimensional representations. So what are the infinite dimensional representations? Now, it's not easy to work them out, but thanks to the mathematicians, they've done the job for us. And I'll just give you some basic facts about infinite dimensional representations. And not today, but maybe tomorrow or the day after, I'll even do something more explicit in the way they can be written down as functions on spin of space and stuff like that. But here we just need the basics. The key point is that there are two Casimir. So the unitary representation are going to be infinite dimensional and labeled by two quantum numbers. Remember that for SU2, the representation labeled by J, and in the J representation you have a basis M. So the representation is given by dJmn matrices function of the SU2 group element. For SL2C, you will have two numbers labeling the representation, and one of these has to be continuous because the group is non-compact. That's where and it's called P, and the other one happened to be discrete. So this is a real number, and this is a half integer. Okay, they're labeled by two numbers, like these are labeled by that. So instead of J, you have PK. Okay, and then we want a basis. And to write a basis in the PK representation is very easy, because there is a theorem that says that the representation here is defined on a Hilbert space now, because this is unitary, PK. So this is infinite dimensional. It carries a representation, so we'll have suitable matrices. And obviously, since it is a representation of SL2C, it's also a representation of SU2 in particular. So you can take this and decompose in SU2 irreducible. So this necessarily has to be a sum of SU2 irreducible. And now you ask a mathematician, and they tell you that each spin J SU2 irreducible is contained only once, no more, and is once or zero, and once if J is larger than K. So it's a sum of J going from K to infinity of the spaces here. So you can think of this as a huge vector which has components, and these matrices for SL2C mix everything, but if you restrict to SU2, they don't mix this HJ components. And that immediately gives you an obvious way to write a basis here, because you have basis element labeled by J, and within each J you can diagonalize LZ. And so this is a basis, it's called the canonical basis. And you look in the books, and you get dpk j m j prime m prime as a function of G, and this is the representation matrices which are written explicitly, and I do not think Mathematica has those ones, but there are explicit formula for this which are not obvious, and some people here are writing paper working explicitly with these quantities here. They are rather complicated objects, that can define with integrals explicitly. They are known, but not simple functions like the Wigner matrices, which are simple functions. Okay. Now the two Casimirs have, like the Casimir of SU2. Remember that. Right here. Remember that the Casimir of SU2 is L square, and C on Jn is just J plus 1 on Jm is diagonal, and is a multiple of the identity on each representation. Is the same for all the representation. So for SL2C, it's going to be the same. So you have two Casimirs, and you have C1 acting on Pk any J, any M is going to be the same. Pk any J and any M multiplied by something, which I'll tell you in a moment, and C2 the same. And what you have here is just something that depends on P and K. And again, you ask a mathematician, and this is P squared minus K squared minus 1, if I don't have it right, and this is minus Pk. Which sort of nice, right? I mean, this is P squared minus K squared, this is Pk, but that's what they are. And the plus 1, minus 1, like minus 1, plus 1 there. Hope is a minus 1 and not a plus 1. Is that minus 1 or plus 1? Does anybody remember? Just look in the books of the science and not trust my science. Okay? And now, I'm not proving any of this, right? It's just stating things that you find in mathematical books. So this is the same. And this is the same. And now, there is a beautiful result. It's not a mathematical book, but it can be derived, and it's pretty nice, which is the following. Take one of these spaces and HPK, and choose a subset of representation with a particular relation between P and K. Okay, choose only those representations where P equal gamma K, where gamma is a real number. You pick a real number gamma, and you choose, you only select a representation where P is gamma K. Okay? And within this, you have all these components here, with J going from K to infinity. Pick the lowest one, the component with J equal K. So in other words, look only for this, so K equal J. So in other words, look only for the states of the form gamma J J, J M. Well, so what? On these states, it happened to be true that K equal gamma L. So if you put here and here one of these states, here and here one of these states, K is gamma L. These are representations, right? So on the representation, the generator act, so K act and L act, they're operators. So they're complicated operators with an explicit formula for them. On the subspace of the representation satisfying that, K equal gamma L.
This complex is going to SL1 subgroup.
I'm sorry?
It's complex, you must choose the SL1 subgroup, not SL2.
It's within this language here, gamma has to be real. If you want a gamma imaginary, you have to change what you're doing, because here you're looking for representation where P and K are related by that.
Yeah.
And the SL2C representation have real P and real half integer K. So within this these definitions, gamma is necessarily real, otherwise you don't know what you're talking about. Which doesn't mean that you can look for something else where with an imaginary gamma you can do something analogous. But in this scheme, this is real, this can only be real. Otherwise, this is no solution. Okay?
I have another question.
Yes.
In the definition of HPK,
Yes.
as a sum of J, I don't think that.
This is a theorem. It's not a definition.
Yeah, see, yes. Of course. But I don't see where P is anymore. I mean, what,
The action of the Jij operators on those states here depends on P. And more precisely, the action of L obviously does not depend on P, because these already know how rotation act on there. But the boosts mix this space one with the other, of course.
and P and
And in their action, P enters explicitly. I mean, in the book there are the formulas for this operator acting on this basis, and you see that there is P inside there. So, if you want, this formula doesn't tell anything about the action of the boosts here. It tells everything about the action of the rotation, but not about the boost. And the boosts mix up the different J. And in the action, in the explicit action, there is P and there is K. Okay. So notice that there's something nice. So I can erase this part here. Yeah. Erase this part here. So if I have an SU2 representation J, the states here are Jm. If you have an SL2C representation Pk, let's put the J upstairs. The states here are Pk, Jm. Now, with these two equations here, I can map one of these into one of these where K is equal J, P is equal gamma J, and I map into the subspace where this J happened to be equal to the J there, right? So there is a map from here to here, which I call Y, which depends on gamma. So let me just put a little gamma so I remember that it depends on gamma, which maps the Jm into gamma J, J, Jm. And it maps as, so it maps sort of, in quotes, it maps SU2 stuff into SL2C stuff. But it maps in an interesting way, namely on its image, K equal gamma L, which happens to be the equation that we will want to be true in gravity once we'll interpret the generator of rotation and boost as operator acting to some suitable space where SL2C is unitary represented.
Sorry, is this true for all the states, or do you take some limit, like large J limit?
There are two ways of doing things. This is true in the large J, well, you're right. It's true in the large J limit if I don't put a +1 here. If I put a +1 here, it's true exactly. It's written in the book and something like that. There are two versions of it. So if I have, I think this +1, if I remember correctly, this is true exactly. It's in the book. And if you don't, it's only true. You're right, in the large J limit. So it's true up to things that will become H-bar terms in the quantum theory. There's no H-bar for the moment. Of course, this is mathematics. But you're right. So, strictly speaking, what I said requires this to be a +1 here. So when gamma is large, it doesn't matter.
Parameter can be complex. It doesn't need to be real.
In the classical theory, you could write a complex parameter, and nothing really changes. And in fact, if you write gamma equal I, and you do the canonical theory, you arrive exactly at the Ashika variables, which is where all this started. Ashika, of course, also considered a real gamma. But with an imaginary gamma, the canonical theory is much simpler. That's why I took an imaginary gamma. And in this way of doing the quantization, a real gamma is turned out to be much simpler. So nowadays, one usually takes gamma real in the theory. The version of the theory with imaginary gamma is still hanging around in the mind of people. But most of the resultant calculation are with gamma real, including both in loop quantum cosmology, in informal results. Okay? So, this Y thing is this Y gamma map here is going to be a play role, going to have a key role in the theory, and I'm going to use it heavily. So I think that next hour I'll be able to write explicitly the transition amplitudes. Transition amplitudes will use this mathematics here. Now, the Y gamma has been written here in a very implicit form, right? Because somehow this is a canonical basis, this is a canonical basis, is defined this way, but the matrix element of the representation on this basis, as I said, are complicated objects. One can go to a different basis, which is more transparent, where the Y has a simpler form. I will maybe do that in the next days when we analyze the classical limit of the theory. For the definition of the theory, the definition of Y is sufficient. So let's stop now a little bit early. So next hour I can get to the total writing down of the transition amplitudes.